Hello, my darlings. So today we're going to look at volumes of solids when we revolve a shape or a curve around an axis, okay? Now, think about volume. When you have a cylinder, as in this yellow shape here, you find the area of a base, which is a circle, so that's pi r squared, and then you multiply by the height, right? Because you think about it, you have all these slices of circles. If you took cross sections, you'd have lots of circle slices, and that's how you find your volume. Same thing here, where we have this triangular prism here. The volume is the area of the base. Notice this base is a triangle. The area of that is 1/2 the base times the altitude, and then we multiply by the height. So whenever we're doing volume, it's always the area of the generator. That's like the cross section. So in the yellow picture, the cross section was a circle, and in the purple picture, the cross section was a triangle, times the height, okay? And really what it is we're adding up all on our interval, all the areas of all the little cross sections. Now notice, once we have that summation, we can think of this as the limit as the number of intervals gets huge of the summation over our interval of our area times our delta x's, and our delta x's are going to get smaller and smaller, and this is the same as the integral from a to b of the area of the cross section times dx. So in order to find the volume of a shape, we're going to integrate from a to b the area of a cross section with respect to x. Now, I'm going to take you to a program that I have, Geometer Sketchpad, and I'm going to help you visualize how when some of these curves are rotated about the x-axis, what the resulting shape looks like. Okay, so here we have half a parabola that we want to rotate around the x-axis. So the first thing I'm going to do is I'm going to show you the reflected area, okay? And that's the first thing we do when we're drawing it on paper. Now, I'm just going to take this rectangle and I'm going to revolve the one rectangle so you can see. And you can see that as that goes around, that's a pretty solid circular disc. Now what I'm going to do, so now I'm going to come over here, same picture, and we are going to revolve the whole area around the x-axis. And you can see how that's spinning to make a three-dimensional solid. And it drew for you one cross section. You can see how the front is a circle, and every cross section, whenever you slice it, you're going to have a circle or a disc. And you can actually slide that through and see that everywhere in that solid, the cross section is a disc. Hope the visualization helps. Okay, so notice now this first box is like the one we saw in the program, okay? And every time we go through it, we're going to have that circular cross section, okay, where the radius is the height of the function. Notice the radius here is the height of the function. If the curve is over in the second box, we revolve this one about the y-axis, but notice this cross-section is still going to be a circle. Now notice over here in these two boxes, if this shape is touching the axis, the x-axis where we're revolving around, we get a dumbbell, and the cross-section is going to be a circle. But if we lift it up so that it's not touching the x-axis, now we don't have a dumbbell with circular cross-sections. Now, see there's a little hole in here. We're going to have what's called a washer. We're not going to worry about washers today, but they are coming. So instead of looking like a dumbbell, it looks more like a spool of thread with that hole in the middle. Okay? All right. So how do we do this? How do we find the volume by the method of slicing, which means we have discs? So there's a few steps. First step, we sketch the solid and a typical cross section. We're going to find a formula for the area of that cross section. Then we're going to find the limits of integration. If we're integrating with respect to x, what values of x do we use from where to where? Then we actually integrate. Okay, now the first example we have here, the region enclosed by the curve y equals sine x plus 2, the line x equals 6, the y-axis and the x-axis is revolved about the x-axis to form a solid. Find the volume of the shape generated. So I'm going to take you to that program again, and I'm going to show you what this one looks like when we revolve it before we try to draw it. Because I'll be honest, the hardest part of this unit for me is drawing the pictures, okay? Okay, so here's the actual graph that we have in this problem. F of x is sine x plus 2, and I have it set at a at 0 and b is at 6. So we're going to revolve around the x-axis, and you can see it almost looks like a vase. But every cross-section, again, is a circular disc. No matter where you slice it, you're going to have a circular disc. So now you've seen on the program what it looks like, and I have these 3 little pictures here to remind you, because not all of us can draw well, some of us can. But now we're going to practice the drawing. So when we draw, the first thing we do is we draw a reflection. So this is about here, this is about here, and I am not looking for perfection. You know I am the last person to judge your drawings. Okay? And when we revolve this, this is going to have a circular opening here. The base here is also circular. And then a cross section that I draw right there is a circle. Okay? And yes, I am going to ask you to draw the pictures. I'm even going to give you points on your test for drawing. Okay? Now it's important to remember that we rotated around the x-axis. Anytime you rotate around the x-axis, you're going to work in terms of x's. And I want you to get in this habit, and I know today it's going to seem redundant because they're all going to be this, but I want you to get in the habit of writing what the cross-section is. The cross-section is a circle or a disc, okay? And how do you find the area of a circle? It's pi r squared. So I want you to get in this habit, even though it's always going to be a circle or a disc and the area is always going to be pi r squared today. But I know where we're going, I know what's coming, and if you start with good habits now, it won't be difficult later on. It makes the later lessons easy. So now our area is pi times the radius squared. What was the radius? This radius starts at the x-axis and goes up to the curve. It doesn't matter where you draw the cross-section. It's always from the x-axis up to the curve, which means the radius is the y value, which is sine x plus 2. And don't forget to square that, okay? Do not, notice the circle, it's a calculator problem. Do not square that out. Your volume is the integral of that area. I'm going to pull the pi out because it's a constant. Sine x plus 2 quantity squared dx. Now our limits. Where did our x's go from? They went from 0 because we started at the y-axis and we ended at x equals 6. The x's are going from 0 to 6. Now you're going to go grab your calculator and you're going to put that in. So our answer here is 85.745 cubic units. So depending on whether or not they give you units, it would be centimeters cubed, liters cubed, whatever it is, okay? So here we are. We finished our first problem. Now when we think about this, we can revolve around the x-axis, which will give us vertical discs. Remember when we talked about area, we talked about vertical strips. Notice these circles, our cross sections are going up and down. They're vertical. So if we have vertical discs, that is the volume is the integral from a to b of pi y squared dx. Notice it's in terms of x. That y squared is the function in terms of x, okay? And it's good to know that when you rotate about the x-axis or any horizontal line, which by the way is parallel to the x-axis, we are doing vertical discs with respect to x. Always, if you rotate around any kind, whether it's the x-axis or any horizontal line, it's always going to be in terms of x. Now, if we use horizontal discs, now the volume is the integral from c to d of pi x squared dy. Now this x is the function in terms of y. And this happens whenever you rotate about the y-axis or any vertical line, which, by the way, is parallel to the y-axis. So anytime you're rotating around a line that looks like this, that's when you're going to work in terms of y. Okay? Here's another problem. The region enclosed by the semicircle, the square root of 16 minus x squared, and the x-axis is revolved about the x-axis to generate a sphere. Find the volume of the sphere. So the first thing I'm going to do is I'm going to draw my semicircle. Remember, this would be like x squared plus y squared equals 16, but we only have the top part. So we're going to go -4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and we have our semicircle. So there's our function, y equals the square root of 16 minus x squared. Now what we're going to do is we're going to reflect it. 1, 2, 3, 4, and we're going to draw the mirror image because we're rotating around the x-axis, which means we're working in terms of x's. Okay, and if we were to slice this, so this is kind of like having an orange, and if you slice the orange and you look at it face on, that's going to have a circular face. Okay, that's because the cross sections are circles or discs, and to find the area of that, it's pi r squared, which means it's pi times, now if you look at this radius, there it is, there's the radius. That's the y value, the height of the curve, and it doesn't matter where you draw the cross section. It's always going to be the height of the curve, y. So you can think of it as pi y squared, but sometimes that part confuses people because we know we want it in terms of the x. So it's the square root of 16 minus x squared, and we're going to square that. Now, when we square a square root, we know that's just going to give us 16 minus x squared, right? Notice this is not a calculator problem. So our volume, we're going to integrate this area formula. I'm going to put the pi outside. 16 minus x squared dx. Now, what are our limits? Our x's went from -4 over here to 4 over here. And now we're ready to integrate. So we keep the pi. The antiderivative of 16 is 16x minus the antiderivative of x squared is x cubed over 3, evaluated from -4 to 4. So this is going to give us pi times. Now if I substitute in the 4, 16 times 4 is 64, minus 4 cubed is 64 over 3, minus, now I'm going to plug in the lower limit, -4. 16 times -4 is -64, minus -4 cubed is a negative, so that's going to make it plus 64 thirds. Okay, and if I combine like terms here, remember this minus will make this positive and this negative. Okay, I'm going to have 64 and 64 is 128, and -64 thirds minus 64 thirds is minus 128 thirds. So that's going to be pi times, and if I have 128 and I subtract a third of 128, that means I'm going to have 2/3 of 128 left over, which is going to give me 256 pi over 3. This answer is fine, it's perfect. If it's on a calculator question though, I just want you to know, some people will put just the integral in the calculator and their answer would be 85.333 pi. That's fine. Some people will put the pi in the calculator and then their answer is 268.083. Just be careful. If you don't put the pi in, make sure the pi is in your answer. If you put the pi into the calculator, make sure it's not in your answer. Okay? Here's another one. The region enclosed by the curve y equals x squared minus 4, the line y equals 4, and the y-axis is revolved about the y-axis to form a solid. Find the volume of the solid shape generated. So the first thing I'm going to do is I'm going to start graphing. So this starts at 0. Now I know I'm going to go over 1 and up a fourth, over 1 up 3/4. All right, and I'm going to come over here, also we have this line y equals 4, and guess what? This is nice because this is where we're going to end up. Now keep in mind here, we are revolving around the y-axis, which means we are working in terms of y. Now when we rotate, it's going to look like this solid shape, but notice this should be solid in here. This is all filled in. It's not an open bowl, okay? It's all filled in. So that you have to be careful of. So what we're going to do, we're going to draw the mirror image. Okay, now remember, this now is a circular opening up top, and the cross section is also a circle where the radius is over here, and that's the x value. Okay, so we have a cross section that is a circle or a disk, and the area is pi r squared. But in this case, our radius is x. We don't have our equation in terms of x. If y equals x squared over 4, that means 4y equals x squared, and x equals, we only had the part on the right-hand side, so when we take the square root to the positive, the square root of 4y, which we could write as 2 radical y, right? That's the same thing. Doesn't matter which way you write it, because now we're going to put it in the area formula. Pi times our radius is the square root of 4y squared, which is going to give us 4 pi times y. Now we're ready to do our volume. Our volume is the integral of our area, 4 pi y. I put the constant 4 pi outside. We're doing this with respect to y. Now our y's started at 0, and then they went up to this height, which was 4. Remember, y equals 4, so our limits are from 0 to 4. All right, now we integrate. We keep the 4 pi. The antiderivative of y is y squared over 2, evaluated from 0 to 4. Now 4 divided by 2 is 2. Keep the pi. Now I'm going to substitute in 4 squared is 16 minus 0 squared is 0. So we get 32 pi cubic units. And there we go. All right, one more. Let's do another one with y. Okay, because I know those are the tricky ones, because we're not used to graphing that way. All right, so the region enclosed by the curve y equals 4 natural log of x, the line y equals 4, the x-axis and the y-axis. So that's going to put us probably in quadrant 1, because I know that the natural log curve, right, is over here in quadrants 4 and 1. So we're in the first quadrant, and I know this is going to be 0, 1, 2, 3, 4. And if I think about when do these meet, 4 natural log of x equals 4. That means the natural log of x is 1. That means x is e, which is about 3.7. So that's where they're going to meet, right about here. Okay. Now, so remember, this is the region we started with. And we're going to take this region and revolve around the y-axis. So everything we're doing is in terms of y. Notice there are the pictures for you again. And again, this is solid. This is filled in. It's not open. Okay, that's a solid there. So when we do this, we're going to draw the mirror image. And now our cross section, we know that the top is circular. The bottom is also rounded. And any cross section is here and has a radius that is equal to x. So we know that our cross section, again, are circles or discs. And we know the area of that is pi r squared, which again is pi x squared. I need to be in terms of y because we went around the y-axis. So we need to look at this. Y equals 4 natural log of x. We need to solve for x. So we divide both sides by 4, and then we change to log form, and we would have e to the y over 4 equals x. That's our function. So our area is pi times e to the y over 4 squared. Now, it's not a calculator question, so we need to realize that when we square something, we multiply the exponents. So y over 4 times 2 is e to the y over 2. Now we're ready to find the volume. We integrate our area, which is pi e to the y over 2 dy. Now let's look on our graph. Our y's were down here at 0, and they went up here to that line y equals 4. So our limits are from 0 to 4 again. All right, we take the antiderivative, we keep the constant pi. The antiderivative of e to the anything is e to the anything. Now what's the derivative of y to the y over 2? That's 1/2. So we have to divide by 1/2, which is the same as multiplying by 2, and we're going to evaluate from 0 to 4. If you prefer to do a u substitution, okay, your u would be y over 2. Your du dy is 1/2, which means that dy is 2 du. So you would have pi times the integral of e to the u du, bring out the 2. You have to change your limits. If y is 4, that means u is 2. If y is 0, that means u is 0 divided by 2 is 0. So from 0 to 2, and your integral is 2 pi e to the u from 0 to 2. E squared minus e to the 0. So you've got 2 pi times e squared minus 1. Over here, we have 2 pi, and we plug in the 4. It's e squared minus e to the 0. Wow, that sounds familiar. It's the exact same thing. 2 pi times e squared minus 1, and that is our answer in cubic units. All right, my darlings, there we go. So we have taken functions and curves, rotated around the x-axis and the y-axis, where the cross-sections are circles, and we have found the volumes of those solids. Have a great day, guys. Bye.